Hey everyone, and welcome. Today, we're diving into an incredibly powerful technique scientists use to sort the invisible world all around us. It's called capillary electrophoresis. It's a method that brings order to molecular chaos, and you'd be surprised just how much it affects our daily lives. So, let's get right into it.
All right, so let me just start with a big question for you. How in the world do you separate things that are not only microscopic, but are also nearly identical to each other? I mean, it's one of the biggest challenges in chemistry and biology, and the answer? Well, it's surprisingly clever.
To really get the solution, first, we've got to appreciate the problem. We're talking about a true molecular puzzle here.
Just picture this. A complex sample is kind of like a molecular soup. It's jam-packed with different ingredients. You've got proteins, DNA, all sorts of little compounds, and they're all just jumbled together. In this state, they're bouncing around completely at random. Trying to pick one specific type of molecule out of that mess, it's like trying to find one specific grain of salt in a giant sugar bowl. It feels almost impossible.
So how do we bring some order to all that chaos? Well, the secret ingredient, believe it or not, is electricity. Let's see exactly how that works. Now this is where the magic really happens. Look at the left side of this. With no electric field, everything's a mess. Total chaos, right? But on the right, bam, you flip the switch and apply an electric field and something amazing happens. All the positively charged molecules, the ions, they start heading for the negative electrode, the cathode. And of course, the negative ions are drawn to the positive electrode, the anode. All of a sudden, you have directed movement. You have order. And that, in a nutshell, is electrophoresis. It's this simple but incredibly powerful idea of using an electric field to separate molecules based on their charge. This is the engine that drives this entire technique.
But hold on. It's not just about positive versus negative. The separation gets way more sophisticated than that. Think of it like a race, where a bunch of different factors decide who wins. A molecule's charge is like its motivation, how badly it wants to get to the finish line. Its size, though, that's its agility. A highly charged, tiny molecule is going to zip across that finish line first, while a bigger, less charged one is going to lag behind. All these things work together to neatly separate that messy soup into all of its individual parts.
So we've got the principle down, but how does this all work in practice? Let's take a little peek inside the machine that makes it all happen.
The absolute heart of the instrument is this, a fused silica capillary. And when I say tiny, I mean tiny. We're talking an inner diameter of maybe 10 to 100 micrometers. To put that in perspective for you, a single strand of human hair is about 70 micrometers wide. So yeah, we're talking about a microscopic racetrack here.
And this shows you the journey of a sample perfectly. First, a tiny drop of our molecular soup gets put into one end of that capillary. Then, they apply a really high voltage, and the race is on. The different molecules all start moving at their own unique speeds. Finally, as each separate little group crosses the finish line, a detector at the other end logs it, creating this unique fingerprint of what was in the original mixture.
Now, this basic setup is already super powerful, but scientists have developed all these different versions or modes, which turns capillary electrophoresis into this incredibly versatile toolbox for solving all sorts of different puzzles.
Okay, so here's a common challenge. What if you want to separate really big molecules, like DNA? Well, in an open tube, they all kind of move at the same speed, no matter how big they are, which, isn't very helpful if you're trying to separate them by size.
The tool for this job is called capillary gel electrophoresis. What scientists do is fill that tiny capillary with a gel, which basically acts like a molecular obstacle course. Or maybe a better word is a sieve. Now, the smaller DNA pieces can wiggle through the pores in that gel pretty easily, while the bigger ones get tangled up and move a lot slower. And just like that, problem solved.
But what about an even tougher problem? What if your molecules have no charge at all? An electric field won't do anything to them. They're just going to sit there. Are they impossible to separate?
Not even close. For this, scientists use a really clever tool called MEKC, or micellar electrokinetic capillary electrophoresis. The trick is to add a detergent, which forms these tiny charged spheres called micelles. You can literally think of these micelles as a taxi service. The uncharged molecules can hop in and out of these little taxis, and since the taxis themselves are moving in the electric field, they carry the uncharged molecules along for the ride. They get separated based on how much time they spend hitching that ride. It's just brilliant.
And trust me, the toolbox is even bigger than that. There are specialized modes to separate molecules based on their acidity, hybrid methods that combine this with other powerful techniques, even ways to analyze molecules that don't dissolve in water.
And get this, there's even a tool to separate enantiomers. These are molecules that are perfect mirror images of each other, which is a notoriously difficult thing to do in chemistry.
So this is all fascinating science for sure, but why does it actually matter to us? Well, this technique has moved way beyond the research lab. It's now making a real impact on our daily lives.
I mean, just take a look at this list. From making sure our food is safe, to developing new medicines, to checking for pollutants in our environment, capillary electrophoresis is there. In forensics, it's a total cornerstone technology. It can separate tiny fragments of DNA, helping to solve crimes. It really is the quiet workhorse of modern science, just humming away behind the scenes.
And to think, it all started with a simple but totally brilliant innovation. As the source material points out, the real game changer was swapping a big, bulky glass U-tube with that tiny capillary we talked about. Now here's the so what. That super thin capillary has a massive surface-to-volume ratio. That means it can get rid of heat really, really well, which allows scientists to crank up the voltage way higher. And higher voltage means a faster race, and a faster race means a much sharper, more precise separation. That one little change unlocked the true power of this method.
Which leaves us with a final, really exciting thought. Capillary electrophoresis gives us the power to see and sort the very building blocks of our world with just incredible precision. So the big question is, what invisible puzzles in medicine, in new materials, in our environment, what puzzles will this technology help us solve next?